Okay, I guess if we wanted to do some exotic examples, I promised a case where the object could potentially be negative. How do you deal with a multi-lens or multi-mirror system? Let's say I've got a lens and I'm not premeditating these, so if they get messed up, sorry. Let's say F1 is, I don't know, 10 centimeters. So we'll be kind of to scale, 2, 4, 6, 8, 10. Here's F1. And I've got another mirror. Let's make it 40 centimeters away. So that would be 10, 2, 4, 6, 8, 10, 10, 10. And what kind do we want to make this one? Oh, let's make it convex, just for simplicity. Doesn't have to be. Okay, and then what else? Let's say that was 2, 4, 6, 8, 10, 2, 4, 6, 8, 20. Here's F2, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. There's F2. All right, and I want to put the object somewhere over here, right? So these are going to be positive because they're convex lenses. All right, I think I've got one that will do what I want this demo to do. So let's say that my object is here at 15 centimeters. Okay, and we will hope that this works out the way we expect it to. How do you deal with a multi-lens system? You don't. Just do each lens individually. Okay, so treat everything according to lens 1 first, and then just kind of see how it works out. So for lens 1, I get 1 over F1 equals 1 over P1 plus 1 over I1. And we want to find all the information about the final image. Okay, so when we do this, I get, I guess, 1 over, we said 10 equals 1 over 15 plus 1 over I1. And that's 3/10, or yeah, 3/30, 2/30. I get I is plus 30 centimeters. And this is exactly the lens that we did in one of the earlier demos. Okay, and then magnification 1 will be minus I over P, or minus 30 over 15, minus 2. Okay, so I need to put that at the 30 centimeter mark. So here's 10, 20, 30. Here's my object, and it's multiplied by a factor of 2 down. This one was 3 high, so 3, 3. There we are. This is image 1. And if we want, we can go fill in the ray diagrams, and maybe we'll do that later. What do we do at this point? If you want to do a multi-lens system, now translate to lens 2. Everything should be relative to lens 2. And we want to treat the last image as the next object. Okay, so what is P2? This is 30 centimeters away from this lens. The second lens is 40 centimeters away, so here's the distance, right? This is the object, object 2, and that'll be 40 centimeters minus 30 equals 10 centimeters. Okay, do all the work again. We get 1 over, let's say F2 is 20 centimeters, equals 1 over the object, that's 10 centimeters, plus 1 over image 2, right? And that's object 2. So we do this, I get 1/10 is 2/20. 1/20 minus 2/20 equals negative 1 over 20. So I2 appears to be minus 20 centimeters from this lens, right? Everything's measured from the second lens for the second lens problem. And then magnification 2 is minus I2 over P2, which is negative 20 over object 2, we said here was 10. That equals plus 2. And this, I think, was exactly the situation we did for the second demo on the lenses. So where is our object located? It is minus 20 centimeters from the second lens. This is 10, 20, here we go. That is image 2 is at that point. And we should multiply the object by a factor of 2 again, right? And it's this one that we're copying, right? So this is going to be 3, 6. And we'll do it again. 3, 6. There we are. I2. So the questions that we need to answer, what's the final location relative to either of the lenses? It's right here. It's at minus 20 centimeters from the second lens, or it's 20 centimeters after the first lens. Whatever they tell you to do for your reference point, you have to use that. How about the final magnification? And why don't I call it capital M for the final magnification? Is it minus 2 plus 2 equals 0? No. We kind of knew what it was here, right? It's doubling that one. In fact, that's what is happening. I take something and plus 2 magnification, something that I already had, right? So this would be a product of the two magnifications, or minus 2 times plus 2 equals minus 4. Is this image real or is it virtual? It's kind of a hard call, right? It's upside down. So is it real because it's upside down, or is it not? Where would you have to put a piece of paper to catch it? If you put it between the two lenses, the light never hits the second lens. So this is your reference for whether the light escapes or does not. Overall, the image is virtual, because this is our 0 point for positive and for negative. And then last question, is it real or inverted? We can see clearly it's inverted by the overall magnification and by the diagram, right? It's clearly upside down. So it is inverted. Okay, some of the taping is going out of order, but we should mention, this is weird, right? That the image is virtual, but it's also upside down, because I thought virtual images were always upright and real were always upside down. That's not necessarily true if you have multiple devices, right? The first one did produce the inversion that we expected. The second one did not produce the inversion that we expected, and that's fine. But the problem is when you have two interactions going at the same time, it's possible to get one or more of these inversions, so the behavior might not be exactly what you expected. But for the single device, look, this one was inverted, and for the second device, this one was not inverted. It did follow exactly the rules for single devices, but when you put them together, now you might get weird results that don't follow those easy rules. So that's a complicated problem, but it's still straightforward, right? You just do one, do the second one, and so on. If I wanted to make the problem really nasty, we could have done something like this and said, here's a lens and a mirror. So how do you do this one? I would do problem 1 for the lens, right? So here's the object, let's say it does that. I would take this and do it with the mirror, so that's a second problem, right? So we would go lens, and then we'd go into the mirror. And I don't know, maybe this will produce a real image, right? So we'll invert it, flip it up like that. So this will be I1, this will be I2. Is that your final answer? Of course not. Once this has happened, the light has switched directions. So now the light is coming that way. So now we have to treat it back through the lens a second time, through the lens again. And that changes, right? For lens 1, this is plus and this is minus. For the mirror, this is plus and this is minus. And then for the lens, this is plus and this is minus. So you have to really pay attention to the sign conventions as you're following the light through the problem. A situation like this, it's possible to get what we call a virtual object. I have said that the object is always going to be positive, except when it's not. So let's say that I did this same problem that we just did, but things ended up being a little bit weird, where this object, let's say that's P1, produces an image over here. This is I1. What would you call the object distance for this lens? The light is still traveling this way, right? So what side is it on? It's not over here. This is a case where P2 is a virtual object. And that means P2 is negative. The first true object, that one's exempt from all the rules, right? It's always going to be plus. But then the ones after that, well, if it lands behind the lens, for lens 2, you have to keep that into consideration and use it. So this would be the only case I can think of if you have a second image that you're treating as a second object that happens to be behind where the light is coming from, then you might have a virtual object.